Hello, Math 1224. This is Dr. P with Lesson Launch 15.3, two kinds of comparison for infinite series. So in this video, which I warn you might run a little bit long because the idea here is complicated, but it is a very worthwhile and important idea. We're going to take a look at these two series that I've written down here, this one and this one, and we're going to try to decide with proof whether these series converge to some finite real number sum or diverge. In this case to infinity, because all the terms in these series are positive. All right. So first of all, I want to recall an idea from earlier in the course that you may remember working with, and that is that we've been down this path before. We've looked at things and tried to determine whether they converge or diverge by comparing them to simpler things. That's going to be the strategy throughout this entire video. Is we're going to try to compare to simpler objects. Simpler objects, because with those we might just know offhand whether those simpler objects, those simpler series in this case, converge or diverge. So recall that we did this with improper integrals. All right. So we're going to try and use this idea now on infinite series. And we're going to start from the same two basic principles as we had before. And those are, if I have some object, either an improper integral or an infinite series, and I know that it's less than something that converges, then I know that the series or integral I'm looking at also converges. So less than convergent is convergent. And I also know, that's principle one. And then principle two is, if I'm looking at some series or integral that I know is greater than another one that I know is divergent, then I know that the series or integral I'm looking at is divergent. So to put it as simply as possible, less than convergent is convergent, greater than divergent is divergent. Those two principles are true of improper integrals, and they're also true of infinite series. All right, so what I'm going to do now, you'll notice I put these in very large text. That's because I'm going to move these over and now start working on this problem over here. So the whole idea of the strategy that we're going to use, we're going to try and determine whether this converges or diverges. And the basic strategy is compare this to something simpler. So what could I think about if I'm looking at 2n minus 1? Let me just write this down. So I'm going to compare the sum from n equals 2 to infinity of 2n minus 1 over n cubed plus 3n. Well, what is something I could compare that to that would be simpler, but would kind of capture the same overall broad behavior? Well, let's see. When I look at this series here, I see a whole bunch of complicated crap, to put it bluntly. But I feel like the crap that matters the most is this. Let me switch colors here. There we go. Yeah, the stuff that matters most seems to me like it's this 2n. As n gets really large, that 2n is going to be much more important than the minus 1. And as n gets really large, this n cubed is going to dwarf the 3n. So my strategy is going to be look at just the series 2n over n cubed, which is the same as the series n equals 2 to infinity of 2 over n squared. Now at this point, I hope that you are thinking of a particular series test that may help us here. Now it might help to rewrite this as 2 times the sum from n equals 2 to infinity of 1 over n squared. Now that should look like something that we have thought about before. Now it was in a more general context, but this is a p-series with p equal to 2. And that's greater than 1, which means this series is convergent. Now that's exciting. Okay, now by the way, one thing I want to clarify here that always comes up when people think about the p-series test and something else, the geometric series test. Those two kind of look like each other in a certain superficial way. Both of them involve powers. So one thing I want to mention is whenever I talk about a p-series, I'm talking about a series where the index of summation, that n, is in the base, and then there is a constant exponent here, a constant, in this case, a 2. A geometric series would be something like 1 over 2 to the n, where the base is constant and then the exponent's variable. So part of the game here is being able to distinguish reliably p-series from geometric series, because those have different tests that you have to pay attention to. I don't mean to go off on a tangent here. It's just something that always comes up. So anyway, based on this little investigation here, I suspect that this thing is convergent. But how do I prove it? Well, to prove it, I would need to show that I have a valid comparison here. I'd need to show that this series here, term by term, is less than the series on the right. So can we prove that? Do we know that that's true? Well, I feel like we're going to be in pretty good shape here, because I think that if I look at the nth term of this series here, 2n minus 1 is smaller than 2n, and I'm dividing by something bigger. N cubed plus 3n is going to be bigger than n cubed. So I think I can make the case. Now I'm just going to write this down verbally, because I feel like all these arguments should have some verbal component to them. We know that for every n, remember this means for every n greater than or equal to 2, since the summation started at 2 anyway, 2n minus 1 over n cubed plus 3n is less than or equal to, and in fact I could say less than if I wanted to. That is less than or equal to 2n over n cubed, because 2n minus 1 is less than 2n, and n cubed plus 3n is bigger than n cubed. So smaller numerator, bigger denominator means that this fraction's value is going to be, at the end of the day, smaller. Okay, so because I know that, and I know that everything here is bigger than 0, and I should have written that at the start. I apologize for not doing that. Really, that's sort of an alignment problem there. That's what I mean to say. For every n greater than or equal to 2, 0 is less than or equal to this here, which is less than or equal to 2n over n cubed. I need the hypothesis that everything is positive, otherwise these comparisons don't always work. Okay, so because that's true, because the sum from n equals 2 to infinity of 2n over n cubed converges by the p-series test, because that converges, we also know that my original sum, the one I wanted to consider, 2n minus 1 over n cubed plus 3n, also converges. Dang tablet screen, it's so small. Also converges, I'm going to need to move this up anyway, also converges by what we call the basic comparison test. Now I realize that's a new name for something that we've been using for a while. But by basic comparison, I just mean using the simple principle that smaller than convergent is convergent and bigger than divergent is divergent. All right? So that's what we're calling the basic comparison test. And I want to have both of these. By the way, I realize I capitalized one and didn't capitalize the other. I'm really not picky about capitalization. In fact, I'm not even consistent myself. But I do want to have both of those things named in your argument, because that's part of putting together a successful argument is naming and calling out the warrants for the claims that you're making. In this case, those warrants are the p-series test and the basic comparison test. Both were important. So that proves, backing out here, that proves that this series here was convergent. All right, so now let's move on to a slightly harder problem. What about this one? 2n plus 1 over n cubed minus 3n. Now, I hope that at this point you are thinking, well, I would really like to compare that with something simpler. And the something simpler that most immediately appeals to me, I don't know about you, but again, it looks like that 2n is the most important piece on top, and in the denominator, the most dominant piece is the n cubed. So again, this is the sum from n equals 2 to infinity of 2 over n squared, which still converges. It's the same thing that we talked about earlier. It still converges by the p-series test. By the way, it's okay to have a constant factor and use the p-series test. There's nothing wrong with that. I just pulled it out on that last example to show that it's really just using that basic principle we talked about last time. So we know that that converges, but think about how a comparison test is going to go. Think about how these series terms compare with these series terms. I have a feeling the world is not going to be quite so kind to me this time. If I jump out and try to make a claim that 2n plus 1 over n cubed minus 3n, that those are smaller than the terms of this convergent series, I have a feeling I'm going to get shot down here. I don't think that's even true. This is false. And in fact, it's sort of patently false, because in this case, my numerator is bigger and my denominator is smaller. That's going to definitely make the value of this rational number here greater than the value of this one. So at this point, I'm kind of stuck. I can do this problem, and in fact, I could do it using a basic comparison, but I would have to get really creative with how I put together this comparison series here. I mean, I could probably do it by doing something like, and I'm just sort of spitballing here, I could perhaps make this a 3n, or maybe a 4n, so that this would always be smaller than 4n. And then I could come up with something here like I don't know, maybe a 1/2 or a 1/4 of n cubed, so that this would always be bigger than that. And that would work. And I wouldn't be changing this series except by constant factors, so it'd still be convergent. But God, why do all of that work? Part of the point of doing this kind of formal mathematics, it's not to do more work, it's to set yourself up so that you don't have to do as much work as you go along. So for this, what we're going to do is we're going to talk about the idea that even though this comparison fails, it fails in a way that sort of doesn't matter all that much. And the idea here is one that we call, when we talk about series, it's called limit comparison. The idea is that if these two quantities are roughly the same as each other in the limit as n goes to infinity, then their series should have the same behavior, either both converge or both diverge. So here's a formal statement of the limit comparison test. There we go. The limit comparison test says this. Suppose that the sum from n equals 1 to infinity of a sub n, and I realize I'm starting these with 1 and the others started with 2. The starting point doesn't matter though, really. Suppose that these, the sum of a sub n's and the sum of b sub n's, are series, and the limit... before I get started on that, one more very important thing I need to say here. Suppose they're series and an is greater than 0 and bn is greater than 0 for all n. That's crucial. If that fails, then I can't say what I'm about to say here. So I need my series terms to be positive. And then assume, and this is really the important assumption here, assume that the limit as n goes to infinity of an over bn, assume that this exists, first of all, and is a non-zero positive real number. So assume that limit exists, it's finite, and it's non-zero. And then this is the crazy part. When I first saw this, I thought something like that, something that broad could not possibly be true, but it turns out it is true. Then these series, a sub n from 1 to infinity, and b sub n, either both converge, we'll just write that out, both converge, or both diverge. In other words, they have to do the same thing. Now that doesn't mean, both diverge. My tablet cursor is kind of sloppy there. They got to do the same thing. That does not mean that they will end up having the same sum. That's very important. They don't have the same sum necessarily, and in fact probably won't. But either they both converge or they both diverge. So the really crucial piece, besides the fact that terms of both series have to be positive, and you got to check that, but the really crucial piece is this, that this limit exists and is a non-zero positive real number. Okay, that has to be true. So why would I introduce something like this at this point? Well, The thing I wanted to compare this to, this 2n plus 1 over n cubed minus 3n, I wanted to compare that to this. So I wanted to think of this as my a sub n. A sub n is 2n plus 1 over n cubed minus 3n. And this was my b sub n, the much simpler 2n over n cubed, where I could just set up that series and immediately know that it converges, right? Well, the thing is, I can't make the basic comparison that I want. I know that this converges, and I would love more than anything in the world to be able to say, well, this is smaller, so the series of these must also converge, but they're just not smaller. It's just not the case. You could try value of n and see that that's not the case. But in the limit, as n goes to infinity, this limit here, is going to exist, and I'm going to illustrate that now. So I'm going to write my argument like this. And see, this is, again, I told you this is going to be a longer video, but I think it's worthwhile. I think this is maybe the most powerful series test in the entire world. Although some people would say it's something else that I'm going to introduce later. But I'm going to let a sub n equal 2n minus, what was it, 2n plus 1, I think, over n cubed minus 3n. And then bn equal to 2n over n cubed. Okay? And the first thing I'm going to do is I'm going to say both of these are positive for all n. That's important. I can't use the limit comparison test otherwise. They're both positive for all n. Actually, sorry, I shouldn't say for all n because if n is 1, that's a little bit untrue. So I should say for all n, going back on this thing is a nuisance. Okay, all n greater than or equal to 2. That I can say. Both of those are positive for all n greater than or equal to 2. And what about that limit? The limit, as n goes to infinity, of a sub n over b sub n. Now this is where we have a little bit of a test of your algebra skills here. What is the limit of all this stuff? 2n plus 1 over n cubed minus 3n over 2n over n cubed. Well, let's see. You know the old phrase, ours is not to question y, ours is to invert and multiply. Now I actually do like to question y, but not in the scope of a now 17-minute video about finding limits and convergence of series. It seems a little bit off of the main point here. So I can simplify that expression like that. I'm going to go and put parentheses around this just to very clearly indicate what I'm taking the limit of here. And now I've got the limit as n goes to infinity of, now this is a bit of a pain in the butt, but I think I can multiply that out without too much trouble. That's going to give me 2n to the fourth plus n cubed on top, and then 2n to the fourth minus, God help me, 6n squared in the denominator. And that limit there, well, you know how to find the limit of that. You could do the thing where you multiply the numerator and denominator by 1 over n to the fourth, but I'm just going to use the fact that I know these are polynomials. I know that I can just scan the lead coefficients, and that's going to be my limit. The ratio of those 2 over 2 is going to be 1, and that's the limit. So this means, so by the limit comparison test, both series A sub n and series B sub n. By the way, if you've already introduced both series properly, you're allowed to do this thing where you leave off the all the little indices on the top and bottom of the summation sign, but you have to introduce them formally first, which means at some point I need to see what the starting point is for each one. But both of these converge or both diverge. And we already found by the p-series test p equals 2 greater than 1 that, I feel like I might as well just use the real estate here, sorry about that, that the sum from n equals 2 to infinity of b sub n converges. Remember, that was that sum from from n equals 2 to infinity of 2 over, what was it, n squared. That converges. So by the limit comparison test, the sum of a sub n from n equals 2 to infinity, that also converges. So it doesn't converge by basic comparison, but I can show it converges by limit comparison. Now let me give you the big picture view of what's going on here. Now I'm right up on 20 minutes. I'm going to try and wrap this up. Okay, so here's the big picture. The big picture is I had these two series here, right? Those are the ones I wanted to check out. The big obstacle that got in my way was I knew that this one, the series of B-sub-n's, that converged. I wanted to show this converges, but these were not, strictly speaking, less than these. But what this limit shows here, and this is really the thing I want you to understand about this, what this limit shows, this shows that as n goes to infinity, a sub n is, and this is very much in quotation marks, about as big as b sub n, because the ratio between those is trending towards 1. That means if the ratio of two things is about 1, you think those two things have about the same size. So a sub n and b sub n have about the same size. So if they have about the same size and one of these series converges, then you should expect the series of these also to converge. And that's not a mathematical proof. The proof you would find in a course like real analysis, but I hope that it's at least somewhat persuasive here. So anyway, wow, we covered a lot of ground there and put together a lot of work as usual. There we go. So what we did was we found that this series here, the one I started with over here, that we can show it converges by basic comparison. But for this, we need some heavier machinery. And by the way, the limit comparison test would have worked very easily on this as well. The algebra is not so much different. It's just you end up with some slightly different coefficients here, but the limit's still pretty clearly going to be 1. So my point is that limit comparison is a little bit broader tool. It works for a larger class of examples, but still, if you see a basic comparison that works, well, the write-up is just a lot tidier. Here, I had to do all this work to show that the limit comparison was valid. So it's a bigger tool, but it also takes more power, thinking home improvement 1990s, to use. Okay, anyway, I've had enough fun for one day. I'm going to put this online, and then I will see you in class. And I hope that the pizza will be enough to make up for the length of all these videos. See you soon.